Hello, I am Eemeli Tomberg from UC Luban, and my topic is eternal inflation in primordial black hole models. This work we have been doing together with Kostas Dimopoulos from Lancaster University. It's not out yet, but it should appear in archive in the next few weeks. So I'm here talking of primordial black holes. These are black holes formed by some primordial processes in the very early universe. They are a dark matter candidate and also a possible source for gravitational waves. And for this reason, they have gathered a lot of interest over the recent years. And I'm here talking of a particular formation mechanism for these black holes, that is primordial perturbations from cosmic inflation. So inflation is this era of accelerated cosmic expansion into very early universe that's typically driven by a single scalar field whose motion is dictated by its potential. Here I'm looking at the specific class of inflection point inflation, where the potential has this plateau at large field values, where the field starts in slower inflation, and this is where you generate the small perturbations that you can see in the cosmic microwave background radiation, CMB. But then the field rolls down to this local feature, and there you can produce these larger perturbations that will later form these black holes. If you zoom into the feature, you will see a local minimum followed by a local maximum. When the field rolls over this minimum, its velocity slows down, and this enhances the so-called curvature perturbation, which can have a very peaked power spectrum. And if this peak reaches a value of, say, 10 to minus 2, then you typically have a large abundance of black holes. Now, we are interested in the phenomenon of eternal inflation in these models. So the idea is that these large quantum fluctuations that give you the big pHs, in some rare patches, they can actually be so strong that they counteract your classical drift. So these patches, they kind of stay inflating for a long time before reheating. And because inflating regions grow fast, these patches can kind of stay dominant in the volume up until late times. And if this happens, if these inflating patches indeed do dominate, then inflation is eternal in the sense that most of the universe is always inflating. Why is this interesting? Well, eternal inflation has implications for the global structure of the spacetime, which becomes a fractal, and it can also affect the observational predictions of, say, the CMB or large-scale structure. So we would like to quantify eternal inflation. We would like to answer the question of what's the inflating volume at late times, and is it non-zero in a given model? We compute this by starting from the probability distribution P for this inflaton field phi at some time n, where the time variable n is the number of e-folds of expansion. We multiply this by e to the power of 3n. This is a volume factor, the scale factor cubed, and we integrate over all of the field values where inflation happens. So phi end here is the kind of end of inflation field value. So this is the expected volume of a patch that starts with the unit volume. And if you go to the late times, then you can check whether this is zero or non-zero. And if it's non-zero, then we say that inflation is eternal. We can solve this P from the so-called Fokker-Planck equation, which is the evolution equation for this P. And this can be derived using stochastic inflation, which is the kind of mathematical construction that takes into account these two things that I mentioned earlier. So you have this classical drift mu given by the derivative of your potential, and then you have this drift sigma from the quantum fluctuations, which kind of moves your field back and forth around these classical trajectories. We solve this equation with the absorbing boundary condition at phi end, so that once a patch exits inflation, it can no longer go back. And because of this absorbing condition, this P goes down over time. It actually typically decays exponentially with some exponent lambda. So these are the so-called exponential tails, well known in this literature. If you plug this into your eternal inflation condition, then you end up with this result where you're comparing the expansion of these patches to this decay exponent lambda. And if this is positive, then you can see that the volume stays non-zero, and eternal inflation happens. In other words, if this lambda is less than or equal to 3, then you have eternal inflation. Now, in principle, with this, you can check any given model, just solve its Fokker-Planck equation, find this lambda at late times, and compare it to 3. However, in practice, there are some problems. First of all, these features that we are interested in, they typically correspond to very short field intervals compared to the full interesting field regime. This can be a problem for numerical solution because of this disparity between scales. Also, eternal inflation actually does usually happen in these models at very large field values beyond the CMB, where you have this flat plateau. We are not interested in this region because it's beyond the observable universe. So we would really like to focus on this feature and what happens around it alone. So we zoom into the feature, and there we can actually approximate the potential as a parabola near the minimum or the maximum. This is nice because in such parabolic potential, we have so-called constant inflation, where the forms of these sigma and mu are well known. So sigma is proportional to a Hubble parameter. This is the usual kind of de Sitter stochastic noise multiplied by some order 1 constant roll correction. And mu is just proportional in phi with the second roll parameter given giving the proportionality constant. And we set absorbing boundaries here around the minimum or the maximum at the distance phi b. The idea is that we choose this so that this parabolic approximation is still valid within the whole region. Then we can solve the Fokker-Planck equation with these simple forms for the coefficients. You can have a semi-analytical solution and read off your lambda value. If that's less than 3, then you can say that you have eternal inflation. And you can actually show rigorously that from this condition, it also follows that you have eternal inflation in the full potential. The idea is that here we concentrate on stochastic paths that spend a long time around the feature. If these contribute a finite volume, this is enough to guarantee eternal inflation also in the full general potential. So now we have these 3 constants, and they map to some value of lambda. And we study the whole mapping in our paper, but in practice, only this wide limit is important. So this is the limit where the boundaries are larger than the typical diffusion length scale. Usually this condition is satisfied because this phi is measured in units of the Planck mass, whereas the sigma is a Hubble parameter, which is smaller. In this limit, the lambda takes a particularly simple form. Near the maximum, it's given by this NH slope parameter, typically order 0.1, and near the minimum, it's suppressed almost 0. So this suggests that you usually do have eternal inflation in these models. We have checked this in some example cases from the literature. This is a polynomial potential with the nominal coupling to gravity in the Jordan frame. And if you look at our parameter values, we indeed are in the wide limit, and our lambda values are so small that we do have eternal inflation. Here is another example. This is an alpha attractor construction, but the story is exactly the same. You are in the wide limit, and eternal inflation happens. And here's a third model. This is a string theory-based construction with this kind of Gaussian bump added on top. But again, it's exactly the same, and you have eternal inflation. So based on this, I make the claim that eternal inflation seems to indeed be generic in these models, or at the very least, you need to be very careful when constructing these models if you want to avoid it. So what are the consequences of this? Well, the idea is that this eternal inflation, it happens in these rare regions of space where the local volume grows a lot. This local large volume corresponds to what is known as type 2 perturbations, and we know that these collapse into primordial black holes. So we have these objects that kind of look like black holes from the outside in a reheated universe, but inside these black holes, there's a space that's still inflating and expanding. So one can ask, what does the universe look like if you zoom inside these black holes? Well, here's a picture of that. The U1 region here is your usual reheated universe. Inside it, you have these black circles, which are your black hole event horizons. And inside some rare black holes, you have eternal inflation given by this gray region E here. So this is where the field kind of gets stuck near the feature for a long time. Each patch in this E space will eventually exit due to the stochastic motion it can exit in two ways, either down the potential towards the reheating or up the potential towards the original CMP. If you go down, you end up in what I call the U2 universe. And if an observer in this universe looks at the sky back at the inflationary history, 50 to 60 folds, what they see is not the original CMP, but instead this eternally inflating region where the field spent a long amount of time. And this is kind of a problem because this E region is very volatile, non-perturbative. So the sky of this U2 universe really doesn't match our very smooth CMP observation. So if you go to the other direction, up the potential, you will end up in this U3 universe. So you will, first these stochastic kicks will carry you over until some turning point up the potential. And after that, the field turns around and follows the usual trajectory and eventually reheats. And the position of this turning point is important. If it's beyond your original CMP scale, then the U3 universe looks basically the same as the U1. But if the turning point is below the original CMP scale, then also in this U3 universe, the very large scale structure is kind of volatile, non-perturbative, because it starts to drop this E region again. Now, it's worth mentioning that in both these U3 and U2 universes, there are rare patches where you get stuck in this E region again. So you have this like black holes inside black holes and this cyclical fractal structure that is typical of eternal inflation. Okay, so now we can ask which of these universes do we actually expect to find ourselves in? In the spirit of eternal inflation, we can give these universes volume-weighted probabilities. So here, this U1 universe is the least likely because the others kind of branch and grow out of it. For the other universes, the key is that going up the potential is less likely than going down, because to go up, you need these strong quantum perturbations. So by this logic, these large U3 universes are least likely because you need to go all the way to CMP and beyond, whereas these U2 universes are most likely because you are just going down from the very beginning. Now, let me remind you that these two universes are kind of compatible with your CMP, and these two are not because they are so non-perturbative at large scales. To be a bit more precise, this U2 universe probably can't support life because it's so volatile, it probably collapses quite quickly. But there are these U3 universes that are just large enough to form galaxies and life like us, but that still look kind of non-perturbative at large scales. And because of this probability argument, it now kind of seems that we should expect to find ourselves in these small U3 universes. This is a bit of a problem because I'm now kind of arguing that these eternally inflating PPS models, they are incompatible with the CMP. We should expect to see something else than the smooth CMP that we do actually see out the sky. Now, this claim comes with an asterisk, so this is true if you believe in this volume weighting argument. Let me stress that these U1 and U3 large universes, they do still exist in your spacetime. It's just that their volume fraction is very small. So maybe you just are tempted to discard this volume weighting argument and say that it's not a problem. I'm not entirely satisfied with this myself, and the reason is that if you do this, then you can't actually use eternal inflation to solve the initial condition problem for inflation. So the idea is that even if inflation happens so that it starts in only some very rare patches, if these patches inflate eternally, then they will eventually take over the whole volume, and you can claim that inflation is a generic initial condition for the universe. If you abandon this volume weighting argument, then you can't use this logic either. And that brings me to my final slide. So I have shown that eternal inflation is generic in these inflection point primordial black hole models. And I have argued that these models are then incompatible with the CMP observations. That is true if you use this volume weighting. There are some open questions here. In particular, what should we think of this volume weighting in this context? And if you do use it, if this eternal inflation indeed is a problem, then there's the open question of what sort of limits does this place on your kind of model building and the parameter space in these inflection point models. And I would be happy to discuss this further with the participants of the conference. Thank you.